I'm taking a look at these Sunpak LED96 lights. Can catch them on sale for pretty cheap, I guess till they're all gone. It runs off of 4 AA batteries, alkaline or nickel metal hydride. I expect would have to use the rechargeable AA batteries. Alkaline would end up costing a fortune in the long run. So in the box, have the light, a filter, and instructions. Comes with a clear filter in place, not really frosted, just diffuses the light a bit it looks. It's cheap feeling, but the battery door does seem to fit pretty snug. Can mount it with a 1/4 threaded stud, so that's good. Gives some mounting versatility. I'll get some batteries and let's see what the light looks like. A little tough to get the battery door on, but it fits tight. A decent looking white light. Take a look with the clear diffuser. Can still see the individual LEDs, but does help some. The amber diffuser. Takes some of the cold out of the light, probably not of any real use. Now for a bit of color comparison. The chart on the left is illuminated with some 5000K very high CRI LEDs. The chart on the right is illuminated with the Sunpak light. White balance was done for each chart as the Sunpak is around 6300K. I don't know how well this will show up on the video, but the biggest difference I noticed were in the yellow and red squares. But I would say the light output from the Sunpak is quite good. Compared to my 5000K reference LED panel, the Sunpak light puts out quite a bit more light, and I've seen the Sunpak light for sale for well under $20. Give up a bit of color fidelity for a lot less money, but isn't that the way it always is? Okay, let's see what makes this thing tick. There are 6 small Phillips screws holding it together. No plastic clips. That I really appreciate. Really short, thin wires. So all the LEDs are in parallel. That's interesting. I'll have to do a low current test to see how well matched the LEDs are. First off, I'm going to see what kind of current it pulls. It's a pretty bright light. Wow, 1.8 amps. Those AA batteries won't last long at all at that rate. 300 milliamps on the low end. Could run that off a set of alkaline batteries, but at full brightness, alkaline would be a bad choice. I doubt could get 15 minutes out of a set. Definitely, for this to be useful, nickel metal hydride batteries would be the way to go. I'll put it on a DC supply and see what it pulls. At 6 volts, pulls the same as the batteries. If I up the voltage a bit, it pulls a little less current. So we must have a switching regulator in here. I'll dig a bit deeper. Yep, there it is. That little power inductor gives it away. Is that a 555 timer chip? It looks like it. Going to have to dig into why that is there. The LED PC board is pretty straightforward. 96 5mm LEDs in parallel. But that does make me curious about how well matched are the LEDs. So here I'm running about 0.1 milliamps to the panel from a DC power supply. Quite frankly, I'm astonished. The forward voltage drop matching of the LEDs is just about perfect. I think the maker of this panel would have to be doing additional binning over what comes from the LED manufacturer, or they're paying a premium for the LEDs, and I doubt that to be the case. That is amazing. Well done. So here's a schematic I drew up of the PC board. This IC is an AX2002. It's an up to 2 amp step-down regulator made for driving LEDs. It's what you would expect to find in something like this. Now U2 here is an NE555 timer, and I wouldn't expect to see an IC designed in the early 1970s to be here. While the 555 timer may be one of the most brilliantly designed ICs of all time, we will see in a bit why it should not be in this circuit. The current supplied to the LEDs is set by the voltage drop across these resistors. they work out to be about 123 milliohms. And from the formula in the AX2002 datasheet, that gives about 2 amps of output to the LEDs. So running the chip wide open, and why not? That's what it's made for. Can see the output is well filtered, if we ignore the type of caps used anyway. So should give a nice clean even current to the LEDs. So far, so good. Now Q1 here is where things go off the rails. I don't know for sure, but Q1 is most likely an N-channel MOSFET. And its gate is driven from the 555 timer. And the 555 timer is controlled by VR1, the brightness control. Here's the waveform of the Q1 gate at about mid-intensity. So they decide to take a very nice clean constant current to the LEDs. Hey, let's just flash them on and off to reduce the brightness. We'll just flash them very fast and no one will notice. This light is sold for video and photography, so in my opinion this circuit here is a complete design failure. There should be no flashing of the LEDs for this type of light, period. Let's see what kind of efficiency we get out of this thing. The voltage to the panel at minimum brightness is about 2.4 volts. And at maximum brightness, about 3.2 volts. I'll take some LED current readings. At minimum brightness, it pulls about 80 milliamps. So at low brightness, this thing is horribly inefficient. About 200 milliwatts to the LEDs while pulling about 1.8 watts. I hope the 20 kHz switching is messing up these readings, and it's not really that bad. At maximum brightness, close to 2 amps, right in line with the feedback resistor calculations. And the efficiency is better, but still not great. A little over 6 watts to the LEDs, and pulling a little over 9 watts from the power supply. And there is no switching here to mess up any readings. Not so good. I'll do a little test of the light output. Just a little photodiode and transistor circuit to detect the light level. At maximum brightness, my circuit is fully on and the output voltage is about 0 volts. And as I turn the light away from the photodiode, the voltage goes up to a little over 11 volts. Now as I start to turn the brightness down, can see the 20 kHz drop in light output. Now the light output is not a square wave. I'm not sure if that is because of the LED phosphorus decay time, or because of capacitor C13. Either way, light output is dropping almost to the dark level, at a 20 kHz rate. And that could really be a problem if you have a newer camera with a fast electronic shutter. As I turn the brightness down to the minimum, the light level when the LED is on does drop, but when the LED is off, the light drops all the way into the dark level. There is just no need for that. Bad design. It really seems like a lot of effort was put into making a very nice LED panel. 96 extremely well matched LEDs, and that is no easy task. I'm really impressed with the LED panel. At the same time, the driver circuit for the LEDs is horrible. Efficiency is well below where it should be. Under 70% at full brightness, that's just not good. Battery energy is precious, and this is just flushing electrons down the drain. At less than full brightness, what can I say? It's not a light, it's a 20 kHz strobe light with really horrible efficiency. But everything is relative to price. I think the LED panel is probably worth $20. Seems to be very nice LEDs. Does it give off useful light? Yes, with some exceptions. Might be a problem if using 2 of them together and not at full brightness. To sum it up, I don't like photo lights that flash. Can and is it worth fixing? Maybe. Stay tuned. Thank you for watching.